Okay, so we are starting. This is my third take because I keep getting random phone calls. Again, we are reviewing so far what we've done in strengths. When we cut a system, I'm going to say a beam, but it could be a shaft and torsion. It doesn't matter. When we cut a system, we can have four internal forces. We can have beam shear, we can have bending moment, we can have this normal force, and we can have torque. Okay? This normal force is always perpendicular to my cross section. So if I put this up here now, normal force is always perpendicular to the cross section, and our equation is sigma equals N over A. Okay? It's an average. When I stretch a rubber band, all of those fibers are stretching. This stress is an average on the cross section. So I would have normal tension, and then if I had compression, I might end up calling it compression back onto that cross section. It's important to keep up with positives and negatives because they are talking about behavior. So if I have a positive normal force, that means I'm in tension. I'm going to have a positive stress. Then when I go back and find my delta, I know that it's a positive delta, okay? It's going to be positive because I'm using a positive N. If I have compression, I'm going to assume it's to be positive in tension. If I find out it's negative, it's actually acting in compression, then I have a negative stress because it's that negative N over A. And it's important to keep up with positive stress, negative stress. Positive stress will have a positive change in length. Negative stress will have a negative change in length because I have that negative normal by behavior. Okay. We also, when we looked at this normal force, we looked at like a lap splice that we might have a bolt connection, or we could have glue or whatever. So this normal force, if I then just zoom in on uh, right here, okay, where that connection is, I have a normal force. And because of that normal force, I end up with a shear across that bolt. So this shear across the bolt is still that normal force over now the area of the bolt or bolts or area of the glue. Okay. So if I have a beam and bending that has beam shear, I can draw a shear diagram, and it also has a normal force that's either pulling or pushing. This bolt is going to have a shear stress associated with it. Okay. Now, my bending moment. So this is a bending moment. Okay. And remember, this is positive. Positive bending moment gives me curvature where I have compression tension. Negative bending moment, that's negative, gives me tension compression. So again, it's important to state, is it a positive moment or a negative moment? Because behaviorally, it has compression tension or tension compression, which is very important to understand what's happening where. Our equation is my over I. So m is constant on a cross section. My moment of inertia is constant, but y is, if we're looking at a rectangular section, y is the distance up or down from the centroid. So as we go farther up, y increases, which means that the stress that we have increases as we go up. Okay, so if it's positive moment, then I'm going to have compression up here. And on the bottom, I'm going to have tension because these fibers are really having to stretch and elongate to make this curve happen. These fibers at the top are really having to go into compression to make that curve happen. And so we will see that this is a linear function where right here at the centroid, where we transition from compression to tension or tension to compression, our y equals 0. Right here at this point, y equals 0. So our normal stress right at that point is 0. Okay. Can I have a normal and a bending happening at the same time? Absolutely. Absolutely. So we might have a tension force happening with a bending moment. And I'm going to have to make sure I understand if this is tension, it's positive P over A. If we're bending and compression on the top, then I might have positive P over A minus my over I. And down here, I would still have that positive P over A plus my over I. And again, this is why it's super important to understand, am I working with a positive moment or a negative moment? What is happening? Because if I'm stretching to get around the curve and I'm stretching because I have a tensile force that's happening on there, then I'm actually increasing that normal stress. If I'm decreasing my length at the top to make that curve happen, but I still also have tension, it's not as much in as much compression. So this could be shifted, but at the end of the day, it's always going to be linear. Okay, we've already done torque. Okay, so torque again is shear stress, and it is going to be, if that's the centroid, it is a twisting about its centroid. Sorry, twisting about its centroid. Okay, and we've done torque, we've had torque diagrams, and again, here's my radius. So my shear stress is T rho over J. And much like bending moment, the torque on the cross section is the same. J is my polar moment of inertia. This is my radial length. It is the length of my radius as I move outwards. When I'm at the very center, my radius is 0. As I move along this radial line rho, okay, rho is increasing, therefore my shear stress is increasing. I will have the largest amount of shear stress on the outside. So if I were to draw the shear stress associated, okay, it is going to be a linear change. Linearly, it gets larger as rho increases. So the largest stress is out on those top fibers. And if you think about, I am twisting something and it is rotating, we are rotating about that centroid. It's not rotating, but as we move farther and farther up that radius, as we're trying to twist it, these fibers on the outside, like of your washcloth, you can really see it twisting, are having to twist a whole lot farther. Okay, they're having to twist a whole lot farther to make this stay a composite without having any like tears or shearing in there. Then we have beam shear. This is shear from a beam and bending. Okay, it is a shear of VQ over IT. This one is parabolic because our V is constant. It's from a shear diagram. Our I is constant. Our T is going to be the thickness of whatever point we're looking at. Thickness here or thickness here. Q is, remember, it's the moment of an area. It's the area beyond that fiber. It's the area beyond that fiber. When I get all the way to the bottom, there's no more area beyond that fiber that I'm trying to hold on to. So when I look down here, Q equals 0. Okay, when I look at the very top, there's no material I'm trying to hold on. Q equals 0. We find that the maximum shear stress is now at the center. So it's different than all of the other stresses that we've done. Okay, so this is where I'm going to have the max is right here because here is where Q is the largest. I have the most area beyond that fiber, or I have most area beyond that fiber. And that's why when you look at like a big, if you see giant big wooden beams, you might see some like separation right here in the center where your supports are, because that's the shear, that's that longitudinal shear that's happening. So if we were to take like a little tiny element out, and I were to look at the shear happening on that element, okay, for static equilibrium to happen, I would also have to have a shear equal and opposite on the other side. That causes spinning. So we need this longitudinal shear to keep that block. Okay, so this longitudinal shear is what we're looking at when we are looking at beam shear. Okay, we're going to find on Monday when we start looking at connections with shear that we're going to end up with shear flow equals VQ over I. And this is going to be for connections. Okay, but it's specifically from beam shear. Okay, this is not the tau equals V over A from normal stress. So when you guys are doing homework and as we approach the final, you are really going to need to understand the 4 internal forces, moments, whatever that could happen. And for each one of these, you're going to have to understand the stress equation that goes with it and why it works the way it works, especially when we go back and we start adding our normal stresses because they are additive. And torque and beam shear are additive. They're both shear. Okay. And where could these both happen? Just like the example we did today, we had this shaft that was in these little clips, and it had, like a belts on it. So like you would see, maybe in your car, it turns stuff. Not only do I have shear stress from torsion, but this is now also a beam and bending. So I've introduced bending moment and shear from bending. And we're going to find that we can actually add or subtract our torque and our beam shear depending on which direction each of them are happening. Okay, so this is, you guys really, really, really need to just get this sorted out in your head and then understand each of these stresses, what the equation looks like for that stress, and how it's distributed. Because if you can understand this, then when we start putting it all together and we use superposition, so we can take each load individually, we can take each individual load as it comes when we find our internals, and we know that I can add normal and moment. I can add shear and torque, not literally the numbers, but the stresses associated with them. So you might want to just make a copy of this for yourself, go through it, and make sure you totally, totally understand what is coming from each equation. So when you look at an equation sheet and you see this, you know that, oh, this is torque, this is beam shear, this is bending moment, this is P over A, N over A. Okay, thank you guys very much.